Hello everyone, welcome to the second of our tutorial videos on AI-powered denoising, where we describe how to use deep neural networks to estimate images from data that are corrupted by noise. The first of our videos focused on supervised learning, where we use a dataset of clean and noisy image pairs to train networks to denoise. In this video, we're going to introduce the unsupervised learning paradigm, which allows us to train these networks only using noisy data, which is pretty amazing. Let's take a look. We're going to talk about unsupervised learning, but first let us remind ourselves why we care about the denoising problem. The denoising problem is that of estimating an image from data that are corrupted by noise, like this. And the reason why we care about denoising is that when we acquire data using any imaging device that you can imagine, a camera, a microscope, a telescope, anything, they're always going to be corrupted by noise. This is an example from electron microscopy where we want to study this material, and we can't because we cannot see what is going on because of the intense noise that corrupts the image. This is an electron microscope, so if we were able to see where the material underlying the data, we would see the individual atoms and the atomic structure of the material. In supervised denoising, which we explained in the previous video, what we do is we minimize the mean squared error or some other similar loss or cost function between the denoised output of the network, given a noisy input, and the clean ground truth image that it should produce. But that assumes that we have a training set that consists of clean images and their noisy counterparts. What is the problem? Well, what's the good news first? The good news is that this works very, very well. You can go back to the previous video on supervised learning and see that it produces amazing results. These networks are able to learn very effective denoising strategies directly from the data that are well adapted to a wide range of signals and noise. What's the bad news? The bad news is that this requires clean images so that we can have these clean noisy pairs for training, and often in the real world these are not necessarily available in practice. So what do we do? In this video, I'm going to show you that you can actually just use the noisy data to train a neural network under certain assumptions. And the plan is to first explain the noise-to-noise framework, which essentially shows you why this would be possible in principle. Then we're going to go over different unsupervised methods that can be interpreted as different implementations of this noise-to-noise framework. And finally, we're going to look at some results on real data. Okay, so the noise-to-noise framework. The main insight in unsupervised denoising is that you can actually train a network to approximate a noisy target instead of a clean image. So in supervised learning, here we would have a clean image that we're comparing to the denoised output of the network, and then we perform stochastic gradient descent to change the network parameters little by little so that it denoises. It improves its denoising performance over the different training epochs. Now we're saying, okay, we don't have a clean target that we can compare to. What if we use a noisy target instead? This sounds crazy the first time you hear about it, but let's see why it's actually a pretty good idea. And this idea was introduced in this noise-to-noise paper in 2018. So in order to illustrate why this is a good idea, let's do a little bit of math. So imagine that this is your clean signal X that you want to estimate, and this is your data Y, which is corrupted by some noise Z, okay? You want to train a network that we denote with this big wiggly, not wiggly, like this D letter, to estimate X from the data Y. Usually what we would do is we would take a look at many examples, X1, X2, Xn, and so on, that are paired. So these are clean examples that are paired with their corresponding noisy counterparts, Y1, Y2, Y3, and so on. okay? And then we put them through the network and we compare and we, again, minimize by stochastic gradient descent to improve the network. This is the loss that we're using for training. We cannot do that because we don't have access to these clean excites, to these clean signals. So instead, what we're saying is, what if you have access? And we will see, it's not completely obvious why you might, but in the real world, you can actually get targets like this, and we'll discuss in a moment how you would go about doing it. But for now, just imagine that you had access to a noisy target T, which corresponds to the same clean signal, but corrupted by different noise that is independent from the original noise that corrupts your data. Okay, if you do that, and then you compare the you compare the denoised estimate of the network given this noise with the noisy target computed from the independent noise, then let's see what happens. Okay, this is for a specific example. We have this squared difference. We can expand it in the following way. First, we know that the noisy target corresponds to the same underlying clean image or clean signal with this different noise. We expand it, and now by expanding the squares, we get a term that looks suspiciously like what we want, the mean squared error with respect to the true clean underlying signal. We get another term that only depends on this independent noise. It does not depend on the network output. And we get an additional term, which is the product of the noise with the difference between the clean signal and the network output. So when we average this, or we sum this over many, many examples, which is what we do when we compute the MSE, what happens to this term is that as long as W and C are independent, this is actually going to cancel out. Why? Because we are going to imagine that the noise is zero mean, and when you have the mean of two independent quantities, right? These are the two independent quantities. Just to be clear, we have the mean of these two independent quantities. If these quantities are independent, then the mean of the product is equal to the product of the means. And if we assume that the noise is zero mean, which is a very common assumption, boom, this goes away. And that's amazing, because if that cross term goes away, which again only happens if the noises are independent, and this is very important, then if we minimize this guy, we're essentially minimizing this guy, because you realize that this other term does not depend on the denoiser. So by training the denoiser with these noisy targets, we're actually minimizing the true MSE with respect to the clean signal. Okay, we're actually minimizing the MSE. Of course, this is provided that we have access to noisy targets where the clean signal is the same as in the data and the noise is independent. Under that assumption, this actually works out. So just to be clear, we're not in a supervised framework where we have access to these clean targets that we can compare to minimize the MSE. Instead, we're comparing to a noisy target and minimizing, again, the MSE, but with respect to the noisy target, which is a good proxy for the true MSE, as long as the noisy target corresponds to the same clean signal X with independent noise. Now, I'm going to show you what happens on three very different types of signals if we apply this paradigm. We already showed you in the video on supervised learning that the supervised denoisers actually work very well for these three types of signals. They're implemented using a 1D convolutional neural network for these guys, 2D convolutional neural network for the natural images, and a UNet, which is a multi-resolution 2D convolutional network for the electron microscopy data. So these are the 1D piecewise constant functions. If we train a supervised denoiser using clean noisy pairs, it does very well. Okay, this is the noisy data. This is the supervised denoising. It does extremely well. If you train using only noisy pairs where the assumptions of noise to noise actually hold, then it does essentially the same, which is quite impressive. So this shows that our math was correct, like it's actually equivalent, minimizing the unsupervised MSE and the MSE. Let's see what happens for natural images. This is a synthetic dataset where we have added the noise ourselves. What we observe is the supervised denoiser does amazing. Again, it had access to clean and noisy pairs during training, but the unsupervised denoising actually does almost equally well, only having access to noisy pairs. It does slightly worse, and I'm going to explain now why this is not a surprise, because when we get to the electron microscopy data, we actually observe that this is the noisy data. These data are extremely noisy to mimic a realistic situation where you're acquiring data with the electron microscope. The supervised denoiser works extremely well. The unsupervised denoiser works less well. And this is because this dataset is actually relatively small. We see this in other types of signals. Also, if we have a small training set, the unsupervised, minimizing the unsupervised loss function, cost function does not achieve like the same level of accurate denoising than in the supervised case. But when we have large training sets, the performance is equivalent. So unsupervised methods typically need more data. You need to do to go over more and more examples in order to be able to learn the same structure as from a clean noisy pair. So there is a trade-off here. It's not magic. You can exploit this unsupervised cost function, but you're going to need larger training data sets. And this is why we observe worse results for our electron microscopy data. Interestingly, maybe you were thinking about this when I was showing you that the MSE is essentially equivalent to this unsupervised loss. Maybe we can also use this for evaluation, right? The only thing that is stopping us from using this for evaluation, of course, you can use it for training, right? You minimize this, and then it's equivalent to minimizing that. But when you look at the actual values, they are going to be different because of this term. So there's a technique by which you can correct that term with an additional correction. Basically, you incorporate an additional correction to eliminate this and have like an estimator of the supervised mean squared error. This is called the unsupervised mean squared error. This correction uses two additional noisy targets. Assuming that the noisy targets also correspond to the true clean image and have independent noise, they actually allow you to get an unbiased and consistent estimator of the mean squared error, which you can use to evaluate only based on noisy data. If you want more details, you can take a look at that paper. Okay, but now let's go back to the actual denoising. I have shown you that this noise-to-noise framework actually works. You can train a network only with noisy data, but now a very natural question arises, which is, sure, we minimize a loss when comparing to this noisy target, but where do we get this noisy target in practice if we want to train a denoiser for a particular kind of signals? It doesn't seem obvious. This is the key challenge. How do we obtain the noisy targets? Ideally, again, for everything to work out, the target needs to correspond to the same signal as the noisy data, but corrupted by independent noise. There are several strategies to achieve this, and these result in different unsupervised methods in the literature. So now we're going to take a look at a few. The most naive possible strategy is you say, okay, I'm going to just put in the same noisy data. So the good news here is that these noisy data do correspond to the same underlying clean signal. Of course they do. The problem is that the noise is not independent at all. In fact, the network can just learn to output the noisy data, and this would minimize the loss perfectly. Interestingly, even though this sounds crazy, it can actually work if you manage to constrain the network to not learn this non-denoising identity function. This is a very fancy way of saying it can just output the noisy input. If you avoid this by constraining the network, this can actually denoise to some extent. And this is what they do in this very famous deep image prior paper from 2018. The problem is that you can then not use more and more flexible and sophisticated networks because eventually they're just going to learn to overfit the noise. But incredibly, this can actually work to some extent. Another strategy is to say, well, if I have several frames where I'm like trying to image the same object, which actually often happens, for example, in electron microscopy, you take several pictures of the same material, then you can use 2 frames acquired successively as the noise input and the target. And this will work out under 2 assumptions. First, the noise is frame-wise independent. And second, the signal changes slowly over time. Of course, if there's like a sudden change in the signal and now you don't have the same underlying signal, you're violating our assumptions for unsupervised learning to work. A similar strategy, but slightly different, that enables you to not have to acquire different images is spatial subsampling, which is a clever technique where you take, let me change the color here. You take, for every 4 pixels, you kind of assign each of them to a different sub-image. And this gives you 4 sub-images. And then assuming that your clean image, assuming that the noise is pixel-wise independent and the image is smooth, so that when you separate it by this spatial subsampling, you're not distorting it too much, then you're going to have 4 mini images where the underlying clean image is the same and the noise is independent. This is called neighbor to neighbor. That was our third strategy, spatial sampling. There's a 4th strategy that is also very clever, where you say, well, what is the problem with having the same noisy data here? For every specific noisy pixel, the network can just learn to take that pixel and just propagate it to the end and not learn to denoise. But what if you don't give access to the network to that specific noisy pixel, but you give it access to the rest of the image? Then, as long as the noise in the rest of the image is independent, so again we have pixel-wise independence, and as long as the image is smooth, so you can actually reliably denoise a pixel without seeing that specific noisy pixel just from its surroundings, then this can work. This is called blind spot denoising, and it will work again under the assumptions that your noise is pixel-wise independent, because you are not giving, because you need the noise here to be independent from the noise that it's in the data that it's actually using, which is all the other pixels. And you need the signal to be spatially smooth because you need to try to estimate it without having access to that specific noisy pixel. Okay, I do want to say that in practice then, what you do in the end is you do a weighted average with the original noisy pixel often, which improves the denoising a little bit. But those are just details about implementation. So 2 possible implementations of this framework are, first, just masking the pixel, applying, like putting in random noise in the input so that the network cannot use it. And there are 2 papers that use this strategy. And there's another way, which is imposing the blind spot in the actual network architecture, which in our experiments maybe works slightly better, at least in our experience with these methods. But again, both strategies are a way of implementing the same idea, where you have a blind spot in your network. You don't allow it to use the specific noisy pixel that it's estimating, so that it cannot just learn the identity function that does not denoise. And that's it for the different possible strategies for implementing the noise-to-noise framework that enables us to perform unsupervised denoising. And now let's get to the real data. These are real data obtained with an electron microscope that essentially shoots electrons into the material so that we can see the individual atoms. We'll talk a little bit more about the significance of this kind of data in our third video, which focuses on electron microscopy. But here, let's take a look at what happens when we apply unsupervised denoising. I have gone on and on about how the noise has to be spatially independent if you're applying something like neighbor to neighbor or blind spot. Here, it's not completely spatially independent, but the correlation does go down quite a bit. This is basically correlations computed in a vacuum where we know that there's no underlying signal. So this gives us a pretty good idea about how the pixel-wise correlation is. And then if you go 2 pixels away, the noise is actually quite independent. We exploited this for evaluation by subsampling the data spatially. And here are the results. So this is the noisy data. This is what happens if you apply a traditional linear shift invariant filter. It has a tough time, but you can't really blame the filter here very much because the data are really, really tough. Essentially, the problem here is that we cannot shoot a lot of electrons into the material without frying the material, and that's problematic because we want to see how the atomic structure in the material changes in different circumstances. So you're basically limited as to the electron dose that you can put into the material. The equivalent would be how much light you have when you're taking pictures. Here we would have very little light, very few electrons. And because of that, the data are super, super noisy. So, the linear, this Gaussian smoothing, which is a linear shift invariant filter, does not do very well. Neighbor to neighbor actually does quite spectacularly. It manages to find the periodic patterns in the data very well. And in fact, we can apply this unsupervised MSE framework. We take a logarithm to compute the signal-to-noise ratio as opposed to just the MSE, but it's exactly the same idea to evaluate how we're doing. So here we can see that we're doing a lot better quantitatively to the linear filter. This also, by the way, computed in an unsupervised way using the same principle. And visually, we clearly see that here you see the material pretty well, whereas here it's actually very difficult to see. So it works. Here is another example to show you that different methods can actually be applied in practice. The previous one was neighbor to neighbor, where we do this spatial subsampling and then apply the noise-to-noise framework directly. Here, this is the modification to the noise-to-noise framework, where we're not using the individual noisy pixel. We're constraining the network architecture to use the remainder of the pixels. And this is data, which again is highly corrupted by noise. There's a substrate here and there's a nanoparticle, but we can barely see it. When we apply the denoiser, it's quite amazing. It actually manages to figure out that here there's just vacuum. Here there's a periodic substrate, which is recovered quite well. And here there's a nanoparticle, and we even recover, like the atomic structure on the nanoparticle quite accurately. So the conclusions are that we can train and evaluate deep denoisers without access to clean images, which is a game changer for specifically scientific imaging applications where it is unclear what the clean image would actually look like. Most existing methods are strategies to implement the noise-to-noise framework, and we do assume pixel-wise, we do assume noise independence between the noisy target and the output of the network, which can be a challenging practice because noise is actually correlated quite often. So that's really a challenge for future research. For more information, you can take a look at our tutorial on denoising called Learn, Denoise and Discover, a guide to deep denoising with an application to electron microscopy. And I want to thank my wonderful collaborators, Shreyas, Canning, and Peter for working with me on this tutorial. And I also want to acknowledge the support of the National Science Foundation, without whom this work would have been impossible. All right, thank you very much. That's all I got.